Brings me back to the COVID days.
So in 30-1, you learned about the sum and difference identities for trig function, sine, cosine, and tangent. We saw that the sine of a plus b does not equal sine a plus sine b. In 30-1, you saw what that relationship was. Now we're actually going to prove the relationship. So what we're doing here is we've got a unit circle, actually two unit circles. The unit circle on the left has two angles. Angle A and angle B is added directly onto angle A. Remember that at every point on the unit circle you have an x and a y component, and that tells you the cos and the sine. So at point E, that's the point 1, 0. So you've got a rotation angle A that has a terminal arm right here, and so the endpoint there would be cos A, sine A. And then to angle A, we add angle B, and the terminal arm there will be the cosine of A plus B plus, the sine of A plus B. Then we take the second unit circle on the right, and you have the same angle A. So again, the endpoint is cos A sine A. And now instead of adding B onto A like we did in the first circle, in the second circle, we're subtracting B from A. Or we're subtracting B, I guess, from the horizontal positive x-axis. And so that angle there would be the cosine of negative b, the sine of negative b. But remember that this is the C quadrant when you use the cast rule, where cosine is positive. So it'll be the positive cosine of b, the negative sine of b. And so what we have here is we have some similar triangles. Okay? So when I talk about the two triangles that we're looking at, it is triangle in the first diagram. It's the triangle formed from angle A plus angle B. So that is an obtuse triangle, where two of the sides are 1 unit long because these two sides are radii of the circle. And the angle in between them is A plus B. All right? Now, the triangle we're going to look at on the right is also formed by angle A plus angle B. It's this triangle right there, where again, two of the sides are radii of the circle, so they are both 1 unit long, and the angle in between them, once again, is A plus B. So these are similar triangles. They're actually congruent triangles. Similar triangles have the same shape but different size. These triangles are congruent. They have the same shape and the same size because the two sides that are between the angle, or the angles between those two sides, are both 1 unit long. And the angle between them in both cases is A plus B. The only thing that's different is, we'll see they're drawn in different quadrants, right? So in these diagrams, triangle DOE is congruent to triangle FOG. And in brackets it says SAS. That's called the side angle side postulate. If you have two triangles and two sides and the angle in between them are equal, then the other parts must be equal as well. They are congruent triangles. So the longest side, the side across from A plus B, must be equal. So DE, which is the side across from A plus B in the first triangle, must equal FG. Now, these are not drawn to scale, obviously, because it certainly looks like DE is much larger than FG. They're just not drawn to scale. Okay? But the numbers tell us that they should be the same length. Now, we can use the distance formula in order to come up with an expression for both of these sides. And the distance formula is that distance equals the root of y2 minus y1 all squared plus x2 minus x1 all squared. We used this formula before. You might remember we did some questions, some problems, when we were looking at maximum values where we wanted to find a point that was the minimum distance away from a point on a curve, which was a minimum distance away from a point on the y-axis. And we use this distance formula. Now you can switch these two terms around. You can put the x2 minus x1 all squared first. It doesn't really matter. But if we're looking at side DE, so if we said that this one was x2 and y2, and then the 1 comma 0 would be x1 comma y1. So y2 minus y1 would be the sine of a plus b minus 0 all squared. x2 minus x1 would be the cosine of a plus b minus 1 all squared. And that's what this expression here is under the radical. That's that distance formula used there. If we look at this other triangle, where again, if this is point 2, there's x2 and y2, and then this is point 1, so that's x1 and y1. So y2 minus y1 would be the sine of a minus the negative sine of b. x2 minus x1 would be cos a minus cos b. And so that's what this expression here says. That's an expression for the length of FG. And again, these two are equal because they are congruent triangles. So we're going to work with this expression. The first thing I would do is I would square both sides. That eliminates the radicals right off the start. If you square both sides, that eliminates radicals. So this eliminates the radicals. And so now we are going to work down both sides. So this first term, sine of a plus b, take away 0, is just sine of a plus b, and that needs to be squared. So that'll be sine squared a plus b. The second term that's all squared is a binomial. Cos of a plus b is your first term, minus 1 is your second term, so we need to square that. And remember, a shortcut for squaring binomials is square the first term, so that'll be cos squared a plus b. Multiply the two terms together and double, would be minus 2 cos a plus b. And then square the last term, negative 1 squared is plus 1. So there's that term. Now, our Pythagorean identity says that sine squared theta plus cos squared theta equals 1. Remember that one? Sine squared theta plus cos squared theta equals 1, which we can use to simplify these first two terms. This is sine squared theta plus cos squared theta. It doesn't matter what theta is as long as they're the same expression, and they are. So this part here will be 1 minus 2 cos, a plus b plus 1. And the 1 plus 1 gives you 2 minus 2 cos a plus b. So let's leave that there for now. Because on the right side, that equals, when we simplify, not simplify, but when we square this first binomial, remember you will square the first term, multiply the two terms together and double, gives us 2 sine A sine B, and square the last term gives us plus sine squared B. And then the second binomial is also squared. It'll give us a plus cos squared A. Multiply the two terms together and double gives us minus 2 cos A, cos B, and then square the last term gives us plus cos squared B. And we can collect some terms here. For example, let's change the color here. Let's go back to blue. This term here, sine squared A plus cos squared A, will give us 1 from that Pythagorean identity. So we have 1. As well, we have sine squared B plus cos squared B. That also equals 1. So we have plus another 1. And then we have positive 2 sine A sine B minus 2 cos A cos B. So the 1 plus 1 will give us 2 plus 2 sine A sine B minus 2 cos A cos B. And these two expressions are equal. So again, we know that they are equal because they come from congruent triangles. So this is different than when we proved trig identities, where we had to show that they were equal, and because of that we couldn't move things from one side to the other. But in this case we know these two sides are equal, which does allow us to move things from one side to the other. For example, I can subtract 2 from both sides, and those terms of 2 are gone. 2 minus 2 cancels, 2 minus 2 cancels. So we are left with negative 2 cos A plus B equaling 2 sine A sine B minus 2 cos A cos B. And now the two terms on the right as well as the term on the left are all divisible by 2. But because the coefficient in front of the cos A plus B on the left is negative, I'm going to divide everything by negative 2. And that'll give us cos of A plus B on the left equaling, when I divide by negative 2, this first term is going to become negative. The second term is going to become positive, so I'll start with that one. Cos A cos B. And again, this first term, when you divide by negative 2, becomes negative sine A sine B. There's the proof for the sum identity for cosine. We use it extensively in 30-1. Now you see where it comes from. It actually comes from working with those congruent triangles. And you can do the same thing to come up with the sum identity for sine. Okay? You can do the same thing to come up with the sum identity for sine. So let's write the rest of those out. That's the sum identity for cosine. You might remember that the difference identities were derived by changing b to negative b. So if you change b to negative b, this will be cos of A minus b. You change this b to negative b and this b to negative b. What's going to happen is that the cosine of negative b, remember, because I put you in the fourth quadrant, is the positive cosine of b. So that doesn't actually change the first term. But the sine of negative b is the negative sine of b because, again, you're in the fourth quadrant. So that actually changed this term to positive. The cosine of A minus b will equal cos A cos b plus sine A sine b. So there's the difference identity for cosine. Right, we also saw that the sum identity for sine, the sine of a plus b, is sine a cos b plus cos a sine b. And then if you replace b with negative b, that gives us the sine of a minus b. This first term becomes the cos of negative b, which is positive cosine of b, so that first term actually doesn't change. However, when you let b equal negative b, the sine of negative b is the negative sine of b, which gives us negative cos a sine b. There's the sum and difference identities for sine. And we also had sum and difference identities for tangent. The tangent of a plus b, and you can find it by going the sine of a plus b over the cos of a plus b. That will work. But by using this identity, it's just a little easier to work with. That's the tan of a plus the tan of b over 1 minus tan a tan b. That's the sum identity for tangent. The difference identity, the only thing that's different about that is it's the tan of a minus the tan of b over 1 plus tan a tan b. So those are the sum and difference identities. We use them in 30-1 for a couple different applications. One of them was simplifying some expressions involving sum and difference of terms involving sine, cos, and tan. But the other application was finding the exact value of the sine, cos, and tan of angles that are not on the unit circle. That was what we used these for the most. So on the next page, we're asked to find the exact value of the following. The first one being the sine of pi by 12. Pi by 12 is not on the unit circle, but we can use our sum and difference identities to get these answers. So again, let's construct the first quadrant of the unit circle. So this first angle is pi over 6 radians, or 30 degrees. The one at the top is pi over 3 radians, or 60 degrees. The coordinates on the positive x-axis are 1, 0, and the tangent is 0 because it's sine divided by cos. Up at the top, where the coordinates are 0, 1, and remember that the x value tells you the cosine, the y tells you the sine. When you divide sine by cos, 1 over 0 was undefined. So, to get the coordinates at pi on 6, remember, use the hand trick. Pi on 6 is the first angle, which is your second finger, because the little finger actually counts for 0 degrees. So when you put in down this index finger, it's the root of this many fingers over 2, comma, the root of this many fingers over 2. Root 3 over 2, comma, root 1, or 1 over 2. And when you went sine divided by cos, you'll get 1 over root 3, which is root 3 over 3. There's the tangent. At pi on 4, again, put down the middle finger, the root of this many fingers over 2, the root of this many fingers over 2. Yes. The date is the 25th. So it's root 2 over 2, comma, root 2 over 2. And because the tangent is sine over cos, you're dividing something by itself, that gives you 1. Okay. Just make a bit more room here. So at pi on 3 radians, so that's your finger next to your thumb, the root of this many fingers over 2, comma, the root of this many fingers over 2. It's the reverse of pi on 6. It's 1/2, comma, root 3 over 2. And when you divide those, you're going to get root 3. When you divide sine by cos, root 3 over 2 divided by 1/2, you'll get root 3. Okay? So again, we want to find the exact value of sine of pi on 12. If you use your calculator in radian mode, and you do the sine of pi on 12, you'll get an answer, but it's an irrational number, not an exact value. So you can use the calculator to check your answer, but not get it. To get it, we use the unit circle and we use sum and difference identities. So we need to find two angles that either add or subtract. In this case, it has to be subtract because it's 1 pi on 12. Two angles that subtract to get pi on 12, and both of those angles must be on the unit circle. So there'll be, in some cases, a couple different sets of angles that will work. In this case, 4 pi on 12 minus 3 pi on 12 does give you 1 pi on 12. And the reason this works is because when you reduce those angles, it'll be the sine of pi on 3 minus pi on 4. Those two angles are on the unit circle. So to get your expression, you need to use the difference identity for sine, where A is pi on 3, B is pi on 4. So this will be the sine of A times the cosine of B minus the cosine of A times the sine of B. That's the pattern for the difference identity for sine. And these are on your formula sheet. I gave you a copy of the formula sheet last week. These are on there. So you don't have to memorize them. But the unit circle is not, so again, you need to be able to come up with that first quadrant. So the sine of pi on 3. Sine is the y value, root 3 over 2. The sine and cosine of pi on 4 is root 2 over 2. Minus the cosine of pi on 3, which is 1/2. Times the sine of pi on 4, which again is root 2 over 2. So you're going to get root 6 over 4 minus root 2 over 4. And because those have a common denominator, you can combine them. Root 6 minus root 2 all over 4. That should be the exact value of the sine of pi on 12. We already know what the decimal equivalent is, so when we take the answer we got, in brackets, root 6 minus root 2 all over 4, you get the same value. So we just checked it. Our answer is correct, but we were able to write it as an exact value. I'm going to use a calculator. It's no longer exact. It's a decimal that needs to be rounded. Okay? Number 2, the cosine of 5 pi on 12. So I think in this case there's actually 2 ways you can do it. You can go the cosine of, well, there might be more than 2. 2 pi on 12 plus 3 pi on 12, because those two reduce to pi on 6, which is on the unit circle, plus pi on 4, which is also on the unit circle. I think another one that will work, you could go cosine of 8 pi on 12 minus 3 pi on 12. That also gives you 5 pi on 12. So this would be the cosine of, if you multiply top and bottom here by 4, it'll be 2 pi on 3. Now that is on the unit circle, but it's in the second quadrant. But it's fine, it would still work, minus 3 pi on 12, which again reduces to pi on 4. So you could use either of these. It'll look different at the start, but you'll get the same answer at the end. I'm going to use the first one just because that is the one that utilizes angles in the first quadrant. So it is a cosine of pi on 6 plus pi on 4. So we need to use the sum identity for cosine, which is cos A, cos B, minus sine A, sine B. So that is the sum identity for cosine. So the cosine of pi on 6. Cosine is the x value, it's root 3 over 2. Times the cosine of pi on 4, which again is root 2 over 2, minus the sine of pi on 6, which is the y value at pi on 6, that's a half, times the sine on pi on 4, which again is root 2 over 2. So it just so happens we get the same expression as we did on the previous one. Root 3 over 2 times root 2 over 2 minus 1/2 times root 2 over 2. So it's going to be the same answer, root 6 minus root 2 all over 4. And so we know what the decimal should be in our calculator. We've got it in there already. So when we do the cosine of 5 pi on 12, we should get the same decimal. And we do. We do. All right. These next ones are in degrees. So if we're going to check our answer, we have to change the mode of our calculator into degrees. The cosine of 165 is that decimal there. So it's different. But we want to find the exact value, so we need to use sum or difference identities to get that. We need to find two angles that either add or subtract to get 165 degrees, and both of those angles need to be on the unit circle. So in this case, one set of angles that will work would be 135 degrees plus 30 degrees. You see, 135 degrees is halfway between 90 and 180. It has a reference angle of 45 degrees. So it's on the unit circle. In this case, again, we're using the sum identity for cosine, which is cos A, cos B, minus sine A, sine B. Now again, that angle of 135 degrees has a reference angle of 45. It's in the second quadrant, which remember the Castro tells us that is the S quadrant. So the cosine is negative root 2 over 2 times the cosine of 30. The cosine of 30 is root 3 over 2, that's coterminal with pi on 6, minus the sine of 35, which is positive root 2 over 2. Again, it's the sine of 45 degrees in the second quadrant, which is our S quadrant, times the sine of 30, which is 1/2. So this gives us negative root 6 minus root 2 all over 4. Again, you've got a common denominator of 4 there, so you can combine the numerators. And just to check that, on our calculator, if we put the exact value in, we know we need to get that decimal above, negative 0.9659, etc. So negative 6 minus root 2 all over 4, same decimal. Right? So you should never get these wrong because you can always check your answers. Should never get these wrong. Number 4 wants to give the exact value of the tan of 15 degrees. So that could be done by going the tan of 45 degrees minus 30 degrees. 45 minus 30 gives us 15. We can check on our calculator what decimal we should get at the end. Should be that decimal there. But again, that is an irrational number. We want to write it as an exact value, so that's where our sum and difference identities come in. The tan of A minus B is the tan of A minus the tan of B all over 1 plus tan A times tan B.
What time is it?
Block 1. Block 1.
Yeah.
You're in this class in block 3.
Oh, forgot. Sorry.
She's so excited for lunch already. Right. Okay. I guess we had lunch. That was good lunch. Oh yeah.
The tan of 45 is 1 minus the tan of 30 degrees. That's our root 3 over 3. Over 1 plus 1 times root 3 over 3. So what I would do here is I would multiply all the terms by 3 to get rid of the denominators in the top and the bottom. I'm multiplying by 3, which is the same as 3 over 1. And what that does, it eliminates the denominators that are in both the numerator and the denominator. So what I have left is I have 3 minus root 3 over 3 plus root 3. Which is the answer, but it's not simplified. Remember, you should never leave answers with radicals in the denominator. You need to rationalize the denominator. And because the denominator is a binomial, we rationalize by multiplying bottom and top by the conjugate of the denominator, which would be the same two terms with the opposite sign in between. So we're going to multiply by 3 minus root 3, a binomial, the conjugate of the denominator. That's how we rationalize denominators that are a binomial. So on the top, when we multiply this out, we're going to get 9. The outer products will be negative 3 root 3. The inner will also be minus 3 root 3. They combine to minus 6 root 3. And the last term's a negative times a negative is a positive. Root 3 times 3, root 3 is 3. On the bottom, when you multiply these out, the front terms, 3 times 3 again gives you 9. The outer products would be negative 3 root 3, the inner positive 3 root 3. They cancel. That's why multiplying by the conjugate works, because those terms involving the radicals will always cancel. And the last terms, positive times a negative is a negative. Root 3 times root 3 again is 3. So on top, we will have 12 minus 6 root 3 all over 9 minus 3, which is 6. And now all three terms are divisible by 6. You'll get 2 minus root 3 over 1, or 2 minus root 3. There's the simplified answer for the exact value of tangent of 15 degrees. And we'll check to make sure that that value gives us the same decimal that we have in our calculator when we took the tan of 15, and we do. Same value. So that confirms that our answer is correct. Again, you should never get these wrong because they can always be checked. Okay? We used our sum and difference identities for questions like this as well. So we have two different rotation angles here. Angle A and angle B. So we need to set up two XY axes. Now angle A is between pi and 3 pi on 2. That's in our third quadrant. Where angle B is between pi on 2 and pi. So that's in our second quadrant. So B is between pi on 2 and pi, whereas A is between pi and 3 pi on 2. So we draw our reference triangle by drawing a line straight to the x-axis. And again, angle A, our reference angle, is in the third quadrant between pi and 3 pi on 2. Angle B, the reference angle, is in the second quadrant between pi on 2 and pi. And the sine of A, and sine is opposite over hypotenuse, is negative 4 over 5. Remember, the hypotenuse is always positive. The 4 is negative because you're going downwards from the x-axis. And angle B, the cosine, which is adjacent over hypotenuse, is negative 5 over 13. Cosine is adjacent over hypotenuse. The hypotenuse is always positive. The 5 is negative because you're going left from the origin. So we can use Pythagorean theorem in both cases to find the missing sides, because we're going to need the tangent of A and tangent of B. And tangent is opposite over adjacent. So in the first triangle, we're missing the adjacent side, and the second, we're missing the opposite. So we need to use Pythagorean theorem to find out what the missing sides are. So in the first triangle, if we want to find out what x is, it'll be x squared plus negative 4 squared must equal 5 squared. So x squared plus 16 equals 25, x squared equals 9, and x equals 3. But in this case, it'll be negative 3 because we're going left from the origin. And in the case of the second triangle, we need to find out what the length of y is by using Pythagorean theorem. Y squared plus negative 5 squared equals 13 squared. So y squared plus 25 equals 169. When you subtract 25 from both sides, y squared will equal 144. So y equals 12. And that's a positive 12 because you're going upwards from the x-axis. And again, those signs must satisfy the cast rule. In the third quadrant, that's our T quadrant, tangent is positive, which opposite over adjacent, a negative divided by a negative gives you a positive. The other two are negative. And in the second quadrant, sine is positive, sine is opposite over hypotenuse, those are both positive. The other two ratios, cos and tan, will involve that negative 5 side, so they're both going to be negative. Cast rule is satisfied. But we want to find out what the tangent of A plus B is. So the tangent of A plus B equals tan A plus tan B over 1 minus tan A times tan B. So the tangent of A, opposite over adjacent, would be negative 4 over negative 3, 4/3, plus. Tangent of B, opposite over adjacent, would be 12 over negative 5, or negative 12/5. And that's all over 1 minus the product of those two values. So to add those two fractions together on top, we need a common denominator of 15. Multiply these both by 5. You'll get 20 minus, multiply both of these by 3. You'll get 36 all over 5. And that's all over 1. And it's going to become plus because it's a negative times a negative. 4 times 12 is 48 over 3 times 5, which is 15. Now that can be reduced, and we will. But 20 minus 36 is negative 16 over 5. And that'll be divided by, so the 48 over 15, we can divide top and bottom by 3 and get 16 over 5. And so, on the bottom, it's 1 plus 16 over 5. So 1 with the denominator of 5 will be 5 over 5. So you're going to have negative 16 over 5 divided by 5 plus 16 is 21 over 5. Well, let me just check this. Yeah, that looks right. No, this denominator should have been 15 because I got a common denominator of 15 there. So it's negative 16 over 15. There we go, that's better. So divide by a fraction is done by multiplying by the reciprocal. And we can simplify by dividing top and bottom by 5. And you'll get negative 16 over 63. And there's your answer. And unfortunately, a question like this can't really be checked on the calculator. Well, I guess you could. You could find out what the reference angle A would be by going second function sine of negative 4/5. And that would give you the reference angle. And then you could go second function cos of negative 5 on 13, and that would give you the reference angle. But remember, that would only give you A and B. You still have to use the sum identity and tangent to get the actual answer. Whoops. Okay. So, there's the answer. We did a lot of work in 30-1, proving identities. Prove that the cosine of pi plus x, which is one of the related angle identities that we saw on yesterday's lesson, prove that that is equal to the negative cosine of x. So you need to prove the identity. You can't assume that it's true. You need to prove it. So this is where you cannot move things from one side to the other. You have to work down both sides or in this case, the left side, to get an expression that mirrors the right side. And to do that, you would use the sum identity for cosine. Cosine of A plus B is cos A, cos B minus sine A, sine B. And the reason this works is because at pi radians, the coordinates are 0, 1. So the cosine of pi is 0 minus the sine of pi, which is 1. I'm sorry, I got that backwards. At pi, it's negative 1, 0. I apologize. I was thinking pi over 2 in my head, but it's actually pi. Negative 1, 0. So that's going to change these values. It'll be negative 1. That's the cosine of pi, and 0 is the sine of pi. Negative 1 times cosine is negative cosine x, minus 0 times sine x is 0. That gives us your negative cosine x that you needed. Okay? So this is one way that you could derive all those related angle identities that were given to you on the formula sheet, the ones we looked at yesterday, by using the sum and difference identities. So same thing for question 2. We need to show that the left side is equal to sine x on the right. And here we're using the difference identity for cosine, so it's cos A, cos B plus sine A, sine B. And here we're at pi on 2, where the coordinates are 0, 1. Here the cosine of pi on 2 is 0. And the sine of pi on 2 is 1. 0 times cos x is 0, plus 1 times sine x is sine x. And there we have that one proven. Right? So again, this is one of those related angle identities that's on the formula sheet. Now we see where it comes from. And they can all be derived by using the sum and difference identities. So for practice, you should work on these questions. All of 2, all of 5, all of 7, and then for 10, just questions A through D. I will post those solutions on Google Classroom so that you can check your answers. You should do them for practice. $274.